So Hassan is the head TA for the labs, and he's going to cover essentially FPGAs and the labs. Go ahead.
Yeah, I will start shortly.
Sure.
Just want to make sure that I see the chat window.
Okay.
Okay. Yeah, so in the second part of this lecture today, we will go over the lab sessions that are part of this course. And I will also show you the FPGA that we will be using in those lab sessions, and also give a general information about FPGAs. Okay, so let's first start with some logistics. So this semester, all lectures and lab sessions will be online. We will be using Zoom again for the lab sessions. We will soon share more details about exactly how we will do those. But basically, you will be joining a Zoom meeting, and we will expect you to work on the assignments during these hours, depending on like which session you have already chosen from the from Moodle. Yeah, and basically we will expect you to attend those Zoom sessions during these hours, where you can ask questions to the TAs and get help with the assignments. Yeah, and as I said, we will share more information about how this will work exactly. So I got questions about like using past year grades for the labs. So like we shared a Moodle form for that, where you can choose whether you want to use your past grades or not. But I think some of you missed that. And so if you still want to use your grades, I guess you can send me an email. But so there's a deadline for that, right? So you cannot just decide that after the classes started or to the like end of the semester. So you have to decide it now. I guess like let's set like a hard deadline until like end of this week. So anybody who wants to use their past grades should send me an email until the end of the week. Okay. And so about the partners, so many of you did not like choose partners, did not indicate their partners. We will group you randomly, and we will share that information again later this week. Somebody says, I already decided, but the thing, okay, so it is like, if you have said that you want to use your past grades and you are sure that you have past grades, then it should be okay. There's like nothing to be confirmed. Only one of the partners has to fill the form for the like for telling us who will be your partner. Okay, so that form where you have like 2 names and 2 leggy numbers, only one of you should do that. But for selecting which of these sessions you want to attend, both partners should do that. And obviously, like both partners should choose the same session. And you can either work in person during those lab sessions if you would like to come together, or you can just like communicate in the Zoom meeting. Okay, I assume there are no further questions. And so in this slide, I will talk about the grading of the lab sessions. In total, we have 10 labs and 10 different assignments. You will get 30 points in total. We will be putting lab manuals online on the website. Here's the link. And the grading, you'll get graded for 2 things. First is in-class evaluation. So this is a grade you get based on what percentage of the lab manual you have completed. So you have certain tasks in every manual. So if you complete all of them, you'll get 70% of the grade of like that lab session. And 30% will come from the lab reports. You will also get instructions for that, but if you're curious, you can take a look at the lab reports of the last year. So you can get to that website from this year's website. You will see the link on the left sidebar. Yeah, so you'll be also submitting reports. So you can submit reports later than the deadline, but you will get a 1 point penalty for that. And the deadline for the lab reports will be 2 weeks after the lab session. Okay, so Matthias says, I missed the deadline for the lab enrollment. Is it still possible to do it? Yes, I guess. Just send me an email. Okay, so like we announced this earlier, you can use your past grades, and this is the model of the last year grades, and you can see your grades here. And for questions, we prefer you use Piazza because we have more control on that, and it's easier to handle. But you can also send the email to this list over here, and your emails will be sent to all TAs. Okay, so this was all about all I wanted to talk about the lab logistics. So there might be some questions about like how lab sessions will work, but as I said, we will make that clear later. We will send an announcement on Moodle, also on Piazza. But yeah, it's not complicated. You'll just need to basically attend this Zoom lecture. Okay. Okay, yeah, so let's continue with the next part. What will we learn in the lab sessions? So you have seen this transformation hierarchy multiple times in this class so far. And in the labs, we will work on like all these 3 different layers, logic, microarchitecture, and software hardware interface. Specifically, we will be designing logic gates. We will be designing circuits using logic gates. We will be adding new instructions to a processor, and we will be also writing code using the instruction set architecture or just instructions. Okay, and yeah, so we expect you get hands-on experiments in digital circuit design and implementation, and be comfortable working on all these 3 different layers. Okay. Also, we will expect you to like learn to make trade-offs between performance and area complexity when you are designing hardware. And so in general, we will be doing a lot of hardware prototyping on an FPGA. We will work on some debugging tasks where you try to find what is wrong in the hardware design and learn how to debug these issues in the hardware. We will learn Verilog, which is a hardware description language. So this is sort of like a language we use to describe the hardware that we want to implement. So it's basically an easier way to design complex circuits. And we will learn how a hardware design flow works. And for that, we will be using what we call computer-aided design tools or CAD tools to make some of the tasks automatically. Okay, so like before going over like the lab exercises and telling you about the FPGAs, first I want to tell you where the FPGAs are used in today's systems. So first, here we have Microsoft's Project Brainwave as an example. So Project Brainwave is a deep learning platform for real-time AI inference. In this project, Microsoft is basically using FPGAs to accelerate their deep learning tasks. And you can see their prototype board over here, and we have like a bunch of links if you want to learn more. Okay, second example is Amazon is providing FPGAs, they are literally renting FPGAs in their cloud services, which you can use to accelerate your own applications. And these FPGAs are already used like for many things, including like the areas that I've listed here. Okay, so another example is FPGAs are also used in bioinformatics. Specifically, they're used for DNA sequencing, which is a quite time-consuming task. And yeah, so here's one example where you see a board that has an FPGA and a lot of memory to perform the sequencing of a DNA. There are more examples here in the bioinformatics area. So here you can see two recent works from our group that accelerate different aspects of the DNA sequencing task in general. Okay, another use case of the FPGAs is when you want to interface devices in like more flexible or different way than what the existing systems offer you. And in this example, we use FPGA to implement SoftMC, which stands for soft memory controller, or like software-based memory controller that allows us to access DRAM in like a flexible way. So we can issue any command at any time and have like a full control on like what's going on in the DRAM interface. And this is very helpful to like do research on DRAM to characterize various aspects of the DRAM and like do testing. We also have like a new version of SoftMC which supports DDR4, and this is already used in some papers that I've listed here. Okay. Yeah, so basically FPGA infrastructures enable research into RowHammer, and basically they provide us a deep understanding of the RowHammer problem and help us develop potential solutions. And now let's look at some examples. So 7 years ago, we used like an earlier version of, or researchers used an earlier version of SoftMC to find the RowHammer issue in DRAM. And this was the paper that was published in 2014. And later, last year, we revisited the RowHammer problem and analyzed new devices, like more recent DRAM devices, and showed that the RowHammer problem is getting even more serious, meaning that DRAM devices are getting more vulnerable to RowHammer. And there's also another work called Trespass, and in this work, researchers tried to show that the mechanisms to prevent against RowHammer that the manufacturers implement today are not sufficient to actually protect against all kinds of different hammering patterns that we can do. And in this paper, they show how you can change your DRAM hammering pattern, meaning how you can access the DRAM to still induce bit flips. So there's a question, what are FPGAs? We will come to that. But basically, in a high level, FPGAs are a hardware that is reconfigurable. I will explain about it more quickly. And okay, maybe one last example is FPGAs can also be used to interface different types of memories. And one example here is flash memory. It can be used to characterize and test flash memories and also other types of memories. And this is a more recent paper that summarizes the most recent advances in SSDs, which use flash chips typically. And yeah, so FPGA infrastructures enabled research into flash memory and SSD to improve their reliability, performance, and they provided us deep understanding of the problems in those areas and develop potential solutions. Okay, and I think this is the last example. FPGAs can also be used to accelerate various applications. Here, particularly FPGAs are used in this work to accelerate climate modeling. Yeah, and so here in this paper, if you're interested, you can learn more about how they accelerated tensile computation, which is the essential part of climate modeling. Okay, in the next part, I will go over the lab exercises that we will be doing. But first, let me introduce the FPGA board that we'll be using. Yeah, so this is the FPGA board, and I will go over the components one by one. We have various interfaces that are used to get inputs and also to output something out of the FPGA. And the FPGA is what you see here in the middle. So this is the FPGA chip, and the rest that you see on this board is just some peripherals that we use to get inputs and outputs, as I said. Okay, so we have USB, we have video out, so specifically the VGA interface, We have micro USB, which we'll be using to supply power to this board and also to reprogram the FPGA. We have a power switch to turn the board on, 7-segment display. So this is like some sort of output device, and LEDs again to show some output in terms of like, yeah, just LEDs. So switches, we use switches to like input some data to the FPGA, and similarly, we also use push buttons as input. Okay, and finally, this thing in the middle is the FPGA chip, and in the following slides, I will talk about what is inside the FPGA chips and how we program them. So you'll get like a very high-level understanding of that, hopefully. But before that, I will go over the labs. I will try to explain what kind of tasks you will be responsible for during the lab sessions. So at the end of the lab exercises, when like we are done with all of them, you will learn how to develop a simple 32-bit microprocessor running on an FPGA board. Don't worry, it will not be as complicated as it sounds here, because we will be doing things incrementally, and yeah, you will learn it piece by piece. Okay, so each week we will have a new exercise. Not all exercises will require an FPGA board, and the first exercise is the one that will not require an FPGA board. Okay, so yeah, so you are encouraged to experiment the board on your own, so you don't have to like only use it to do the lab assignments, but you can explore on your own and try new things. So for those who are interested to like work on the board individually, if we end up having some extra boards, we can also give some extra boards to you. So one group can get more than one board potentially, but we cannot promise that. Do we get FPGA boards? Yes, you will get FPGA boards. I will tell you how. And the last thing on this slide is it is not possible to destroy the board by programming it. So this is why we strongly encourage you to like try different things. When you're done with the lab, you can like think of like if you are not sure about like why something is working as it is, and you want to try what will happen if you change something, feel free to do that. Yeah. Okay, yeah, so maybe here I will mention how you will get the FPGA boards. We will announce some time slots in which you can come to the ETH building at ETH and get the board. Okay, so you'll basically have, I guess, 15-minute time slots for which you will register, and one group member will need to come to the ETH building to get the board. And we will most likely do that next week. So we'll have multiple slots and in like on multiple days next week, and we will announce them later this week. What programming language do you use to program the boards? We will mainly use Verilog, but on your own, you are also free to explore other languages like System Verilog or VHDL. Yes, only one person will get the, we will give one board per group, and you will need to figure out basically how you will share that board. It is possible that okay, so you won't need the board until the very last step where you will need to test your design. So it will be okay to like if one student uses the board remotely, right? So you can potentially send your like bit file, the thing that you synthesize after implementing your design. To your partner. So you send the bit file to your partner, and your partner can upload that to the FPGA, and I don't know, like you can just see what's happening from the camera. Yes, we don't need FPGA for the first lab session. You can buy an FPGA yourself. Yeah, so here in the slides we have a link. So the board is called Basys 3. You can look it up online, and yeah, if you want, you can purchase one, but that's not necessary. Okay, I see some other questions, but I will also answer them later in the slides. Okay, so let's start with the first lab. So this is the simplest thing we can do. Like we will start very simple. we will draw a basic circuit. It will be a comparison circuit where we will learn how to compare numbers, basically a circuit that tells whether the first number is smaller or larger than the second number, or whether two numbers are equal to each other. So we will compare two electrical signals because we will be representing numbers as electrical signals and find whether they are the same. And the result output is also one-bit electrical signal, right? So it's 1 or 0, or maybe if you want to indicate whether it's greater or smaller, then yeah, we may need to use more bits. So for this one, no FPGA programming is involved. We will ask you to draw the circuits on paper using the basic logic blocks, which we will learn about later. Okay, and in the second lab, we will do something slightly more involved. We will learn how to design a circuit that performs an addition operation. So this addition circuit will basically add two one-bit numbers. And later, we will design another circuit that reuses this one-bit adder to design a bigger adder. So in this case, it will be a 4-bit adder. So this will be basically where you will learn how to design your circuit in a modular way. Okay, and here as an input, we will use the switches on the board that I showed you previously, and we will display the output on the LEDs. Lab 3. In Lab 3, we will be going deeper on the combinatorial circuits. And yeah, we will basically learn how to display the result of the previous lab where we do the addition operation on a 7-segment display. As like you see here, we will, whatever the result of the addition is, we will display that as a number. Okay, lab 4 is about finite state machines. So like up until this lab, all circuits that we design will be combinational, which means they have no memory. So like the result always changes based on whatever inputs you provide to the circuit. But for the first time in this lab, we will implement circuits that have memories. So what that means, so in this example, you can see like a car that either has its turning left signal on or turning right signal on, or both of them are off. So basically here you can see that we have like 3 states. Each circle represents a different state, and the arrows represent those state transitions. So in order to know in which state the circuit is, we have to implement some sort of a memory that tells, okay, this is this state, or this is the turning right state. Okay, and lab 5, we will learn a bit more about arithmetic operations and how to implement arithmetic operations in hardware. So this will be very first step of designing a full processor. So we will extend the addition operation with some more arithmetic operations. So as an example, in addition to addition, we will do subtraction, multiplication, comparison. We will combine all of them in a single hardware module. And in lab 6, we will be testing this ALU. By the way, I forgot to say ALU stands for Arithmetic and Logic Unit, as I said here, and it refers to a module that can perform multiple arithmetic operations, basically. Okay, so in this lab, we will you'll be testing the ALU. You'll learn how to write a test code that checks different cases for the modules that you have developed. And in lab 7, we will go a bit higher and program the processor that we have implemented using an assembly language. Assembly language is basically programming a processor using the instructions that the instruction set architecture offers. So for example, you can see 2 pieces of codes here that do the same thing. On the left-hand side, you see the high-level C-like code, And what this does is basically it adds together even numbers from starting from 0 until 10, right? And here you see the assembly code doing the same. So you can see that there are like multiple, each line represents a different instruction, and each instruction has like its sort of like operation. So this add immediate represents what kind of operation this is, and also other operands as like source and destination operands, right? So what two numbers should add together and where to write the addition result. Okay, so we will learn about the assembly languages later in the course. Okay, and specifically the task that you will be implementing here, the program you will be implementing using MIPS assembly language will be image manipulation. We will be implementing a simple filter using assembly code. Okay, lab 8. So in lab 8, we will start integrating the pieces together. And I think this will be this lab will be covered in 2 weeks in total, but you will be doing different things in each week. Yeah, and we will learn how a processor is built, and we will complete our first MIPS-like processor design. And again, using assembly language, we will run a snake program, which will do something similar to what you have seen in the slide. So I can just play it again. Okay. Lab 9. On lab 9, we will measure the performance of the processor that we have implemented and also improve its performance by adding new instructions. So previously, like in the processors that we will have until lab 8 will not have these two operations, multiplication and bit shifting. Instead, we will be doing those operations using other instructions. But here in this lab, in lab 9, we will implement these two instructions to make things faster. Okay, to like perform the multiplications much faster than we can do with like addition, for example, by running addition multiple times. Okay. Cool. So I will keep moving, and in the next part we will discuss a bit more about the FPGAs, and I will tell you what's an FPGA finally. So this is the board again that we'll be using, and FPGA is this little chip over here. Okay, so FPGA stands for Field Programmable Gate Array, and FPGA is a software reconfigurable hardware substrate. It contains reconfigurable functions or logic blocks, reconfigurable interconnections of these functions or logic blocks. Basically, this reconfiguration allows us to change how these function blocks are connected to each other, and also reconfigurable input and output. Okay, so and when used well, FPGAs have very big advantages. For example, they provide higher performance than running your program in software on a CPU. And they also provide more flexibility of implementation than dedicated hardware or CPU. And they typically also have a shorter time to market because you don't have to manufacture any chip, but you can just get an FPGA, implement your hardware on it. And yeah, if everything works properly, you're done basically with your application. Okay, so yeah, so basically an FPGA looks something like this, where you have like many logic blocks, many switch blocks or interconnects that determines how these logic blocks are interconnected with each other, and also I/O blocks. So what we do when we say we program an FPGA is we configure these logic blocks and their connections and also I/O blocks to create the hardware that we want and map the programs that we want to run on this hardware. Okay, so yeah, as I mentioned in the previous slide, there are two main building blocks, the logic blocks, or we'll refer to them as like lookup tables here, a bit like simpler version of a logic block, I would say, and also switches, which we use to connect the lookup tables to each other. So basically, when we like zoom into an FPGA, it looks like this. We have a lookup table. We have switches here that that basically make up the interconnects. And basically, depending on how we configure those switches, the outputs and inputs of individual lookup tables are getting connected to like different lookup tables. And if you look inside the lookup table, it is basically just a few bits of memory and a multiplexer. And I will explain a bit more about the multiplexer. But essentially, what it does is it selects one of these like bits over here represented with the yellow rectangles and outputs the result. Okay, and yeah, so you can see here the distribution of these different building blocks in an FPGA chip. So majority of it is just interconnect. Yeah, so let me move on since we don't have too much time left. Okay, so and how do you program those FPGAs, or specifically, let's look at how do you program these lookup tables. So in this example, I'm showing a 3-bit input lookup table. So this means that we have 3 bits to select which of the storage bits we want to output. Okay, so yeah, basically, if this was like 2-bit input lookup table, then we should have only 4 of those storage bits, and yeah, have 2 bits over here at the bottom. Okay, and this blue thing over here is what we call a multiplexer. It chooses one of the 8 data inputs that we have over here. And this we will refer to as a data input, and this as a select input. On the next slide, I will show you an example where we will implement a very simple function and map it to this lookup table. Okay, so let me also mention how this input bits work. So this is basically as input bits that we use to select one of these storage bits, right? And these storage bits have addresses, as you can see here. And depending on what input bits, what 3 bits you provide to the multiplexer, a different storage bit or data input is selected. For instance, if all 3 bits are 0, whatever is written in this data input, it will be the output that you'll see. Okay, so let's get to the example. It will be more clear. But yeah, with 3 bits lookup table, you can implement any function that has 3 bits as an input, that gets 3 bits as an input. And hopefully you will be convinced after this slide that that's true. Okay, so let's implement a function that outputs 1 when there are at least 2 1s in a 3-bit input. In other words, we want a circuit that will output 1 when when at least 2 of the bits of a 3-bit input are 1. Okay, so how you will do that in C, I will show 2 examples. One example is basically going over the bits, the 3 bits one by one. So the input is the 3-bit input, and we AND it with 1 to only access the first bit, right? And add it to the count, which we initially initialize to 0. And later we shift the input by 1 to get to the second bit, and we perform this in a loop 3 times. And if it turns out that all bits that we go over here are 1, so that all of the 3 least significant bits are 1, the count should be equal to 3 at the end, like when we exit this loop, right? And later we have this if, which checks if the count is bigger than 1. If so, it returns 1, otherwise it returns 0. Another way of doing this is if you decode like these numbers over here, let me do that. So 0 will correspond to 0, 0, 0, right? And 1 will be like in binary format, represented like this. 2 is represented like this, and 4 is represented like this. So basically, another way of implementing this in C will be using this switch case statement, where we just hard code all values that have 1 or less than 1 in them. Okay, and in that case, the return value will be 0, otherwise it will be 1. Okay, so how we implement this in hardware or in this lookup table by programming the lookup table will be more similar to the second approach in C. And we will go and basically hard code all values here that we want to be output depending on what are the input bits. So it's pretty straightforward. Since we know like the address of this like one data bit here, like 1 bit storage is this, we should set this value to 0, right? Because here we don't have 2 ones, we have no ones at all. All of the values are 0. Similarly, this should also be 0. This should also be 0. So here, when the 3-bit inputs that we provide to this lookup table are 3 or 0, 1, 1, we have 2 ones, and the output should be 1. That should be outputted in that case. Okay, so you can see that it's straightforward to fill those. Every time we see more than 2 ones, we write 1, otherwise we write 0. Okay, so like basically programming the FPGA to implement such simple circuits, it's pretty easy. But if you want to implement something very complicated or more complicated that will use multiple of these lookup tables, then things are getting real complicated because we need to also think about how to connect these lookup tables to each other. Okay, so actually I had an animation for this. Okay, yeah, so how to implement more complex functions. As I said, it is like a complicated task because like FPGAs are huge and we have many of these lookup tables and switches, and depending on the application, the circuit that we want to implement might be huge. So dealing with such complexity manually is not feasible. Okay, let me also tell you about the modern FPGA architectures a little bit. So I showed you an example of a 3-bit lookup table, but the modern FPGAs typically use some more complicated blocks, and they also use 6-bit lookup tables. But they also like use a lot of like custom hardware cores in the FPGAs. They even implement some simple CPU cores. Well, not very simple, but small, I would say. Okay, and those FPGAs also have megabytes of distributed on-chip memory that can be used in applications. So these are not, this cannot be used like as like to like program your logic, but rather as a storage only. And they also implement special purpose hardware blocks, as I said, and even general purpose processors embedded within the FPGA chip. And this is one example of such an FPGA. This is Xilinx Zyng Ultrascale Plus FPGA. And you can see that it implements various blocks. It implements a memory controller to access DRAM. It implements some high-speed interfaces such as USB, DisplayPort, HDMI, and PCI, and other things. It even encrypts some special blocks to do data encryption and decryption. And here you can see 2 processor cores are also inside the FPGA. Okay, let me quickly go over the advantages and disadvantages of the FPGAs. So algorithm can be directly implemented in hardware, and this helps you avoid the overhead of using an instruction set architecture. And you can like highly specialize your hardware for the application, but in general purpose processors, that's not possible. We are just working with whatever is provided with the like CPU itself. It has low development costs compared to a full custom hardware design. It has short time to market, again, compared to a custom hardware design, but you can argue that like doing everything in software can have even shorter time to market. It's reconfigurable in the field. So if you notice that something is wrong in the design, FPGAs allow reconfiguration, so you can just change the design, fix some bugs, which is not possible on a custom hardware always. I mean, unless you design your hardware for that. Yeah, and FPGAs are useful and usable for many purposes, but it also comes with FPGAs also come with disadvantages. They are not as fast as full custom hardware design, and the reconfigurable comes at a cost. So like to make the hardware configurable, they are paying a lot of area overhead. But on the other hand, if you are implementing a hardware for only a specific task, you may like fabricate a chip that is much smaller than the FPGA, but it can perform only that specific task. Okay, so I will also like to talk about how we program the FPGAs a little bit. So we don't have much time. I will try to go over this very quickly. So as I said, we have many of these resources that we want to use to implement our designs. and they're hard to program manually. And for that reason, we are using CAD tools, and we take advantage of high-level functional description languages such as Verilog. Okay, so this is a typical FPGA design flow. We start with a problem definition. So we decide what is the problem we want to solve, and then we implement a solution, or like we described, a hardware that will solve that problem. And for that, we either use Verilog or VHDL or other even higher level languages. So here, your task will be basically implementing the Verilog code of the hardware design, or of the design that you would like to implement. And logic synthesis, placement and routing, and bitstream generations, those will be handled automatically with the tools that we will be using. And this last step, after this last step, we will get a bit file, which is basically like a binary that you can run on the FPGA. But first you need to, well, I would say not run on the FPGA, but you can use it to program the FPGA. Okay, and for this, we will be using Xilinx Vivado. And this is how what Vivado looks like. Okay, I will explain it a bit more. I will run a short demo slightly after this slide. So yeah, Vivado basically helps you go through the design flow that I showed here. And it also has a embedded simulator that you can use to simulate your hardware design, which will help you to debug and find problems in your design. It provides drivers and graphical interface to easily program the FPGA using the USB table. This is installed in the computer rooms that are listed here, but I guess it's not very practical to go out there and use the software. So we will suggest you to install Vivado on your own laptops, and there are instructions for this on the website when you go to the lab sessions page. Okay. Okay, so I will show you a very short demo, and this demo we will see how to use Vivado to implement some Verilog code and follow the FPGA design flow steps to download the bitstream to the FPGA and run some simple application, which is a keyboard demo. Basically, what this demo will do is when you press any key on the keyboard, it will be displayed on the terminal, and the FPGA will be the hardware piece that will basically process that information that a key is pressed. Okay, and here's the video. Hopefully I can play it. Okay. Wait, I'm not sure if you can hear it.
Yeah, I cannot hear it.
Yeah.
Maybe you can give it to your computer.
I don't know how to share my computer.
What if you turn like use the sound output from your computer directly as opposed to using your headphones?
Yeah, I don't know if that's gonna work because like the microphone is also like on the computer. Okay, share sound. Okay, I figured it out. Oh, actually, there might be nothing to hear. My bad. Okay, I will explain things as the video goes. Okay, so first we start with creating the Vivado project. So as we do like in like other IDEs, maybe we name our project. Here we select an RTL project, and in this step we will select the FPGA that we will be working with. So we will have this information, also the video, a link to the video on the website. So you don't need to memorize any of this, obviously. And after creating the project, we will start with adding the files. So here we won't be implementing the program from scratch, but rather I will go to this link over here where I will download the source files. And okay, I will skip this step where I download the source files, and later we add those source files to the Vivado project. The first thing we add is we add the design files. So these are the actual hardware design that we have. And later we'll add the constraints. So constraints are basically, so these are like location constraints that tells which FPGA pin will be connected to which component on the FPGA board. So specifically here, we will connect the FPGA, the like wires coming out from the FPGA chip to the USB because we will be using, we will be connecting our keyboard to the FPGA using the USB interface, as you will see shortly. But here we just simply generate the bit stream because like we are done with the design, we added all the source files. But obviously in the lab sessions, you will need to write those. You'll basically have to design your module yourself. And here first, we will power up the board. So we are connecting the board to a laptop. So this is how we program it and also how we supply power. We are turning the board on. When we first turn it on, it runs a, like whatever program is installed in its read-only memory. And we connect a keyboard to the FPGA. And I think this is all we needed for the like physical connections of the FPGA board. And the bit file is also generated. Now we program the FPGA using the bit file. So first in the step, you are searching for the FPGA. The system should detect it, that an FPGA is connected to the USB port. And yeah, afterwards, we select the, we select program device and select the bit file that we will use to program the FPGA. And okay, so the FPGA is programmed. So let's see what it does now. So we start at terminal and connect it to the serial interface. So if you don't understand what is this, it's not that important at the moment, but we just connect to the board basically to listen to data incoming from the board. And we can see the ASCII codes that, ASCII code that corresponds to each of these letters. So the first number you see here is the ASCII code of the letter of the key that's pressed on the keyboard. And the second thing you see here is just indicates that that key is released. Okay, so it's like press, and the second line indicates the release of the key. Okay, so this was the demo I wanted to show. I'm sorry that I took a bit longer than I expected, but hopefully this was useful. And the link is on the website if you want to watch this, if you want to watch this demo again. And also you can find all the slides. Okay. Any final questions? But I guess we don't have time.
No, I think if there are any burning questions, we can take a few. Otherwise, we will leave them to Moodle, Piazza, wherever students decide to ask. Somebody is asking, is it similar on Mac OS?
So I think Vivado only runs on Linux and Windows. But on Mac OS, you can either use virtual machine or you can install Windows on that.
Yeah, virtual machine sounds like a good answer. There's another question. I don't know if you see it related to the license.
Yeah. I'll need to check that, but Xilinx should be providing a free license for the board that we are going to use. The license shouldn't be an issue, but yeah, I'll check and update the instructions if needed.
Okay. If you run into any issues, please let Hassan and other TAs know. This should be relatively easy to set up the board and everything.
Yeah, maybe for that purpose, Piazza is a better platform because like other students can also see that.
Exactly, and they can also help you, as we mentioned earlier, right? Some people may figure it out earlier and get to respond earlier also. Okay, well, hopefully you will have fun doing these labs. I think we're done for today. Tomorrow we will start with combinational logic. If you can do the reading on combinational logic, it'll be helpful. You don't have to do it, but if you do the reading, you will see that the lecture is based on the reading also, and you can go deeper perhaps. Okay, thanks Hassan for presenting the labs. And I will see everyone tomorrow.